Let's look at growth where you have an upper limit. So in real situations, a lot of the time you'll have some sort of constraining factor that keeps the growth from taking off to infinity. The examples are cells in a petri dish. They'll grow exponentially to begin with, but later, overcrowding and competition for food, things like that will become a problem, and we wind up having a limit on the growth. And so we wind up getting graphs that look kind of like this, where they start off, if you trace along here, we start off with some small population at the beginning, and then it grows exponentially, or something close to exponentially. But then at a certain point, it hits an inflection point, and the growth starts to slow down. And then it tapers off to some maximum value. And there are different functions that have this sort of shape. Um, the one we're going to look at is called the logistic function, and it has this for its equation. Now, before we delve into this equation and use it to solve some things, I want to look at why this equation has the right form. Let's think about what happens to this value over here when t grows large. I mean, if you look at this, when t grows large, it's approaching, in this case, 100. This number c on top is the capacity. So this graph up here has capacity of 100. A and B determine more of the curvature inside of here. How steep it is, how where it starts off, and so on. So let's look at what happens when t grows large. When t grows large, minus bt goes to a large negative number. And if you look at what happens to e to the minus bt, well, e to the x looks like this. If you take this and you make the thing that you're plugging in up here, e to the x, if you plug in a large negative number, you get something that approaches 0. So as t grows large, this bit right here goes to 0, which makes the whole bit, when you multiply it by a, still goes to 0. And so your denominator approaches 1. So the function value is going to be c over 1, or just c. So that's why c there is the limit. So the limit there, it's also called the capacity or the carrying capacity. Before we do any examples, I want to play with this on Desmos. So here's an example where I've got, I put in 10 for my capacity. You can see over here that 10, as t grows large, this is approaching 10. My A and B, if I start moving them around, they change a little bit about the curve. Let's make A go. Let's let it grow larger. So that helps determine how far out the curve starts to move up. B, if I bring it down to something really small, like say 0.01, well, it almost looks flat. If I change it to 0.1, let me zoom this out a bit so we can see it. We're approaching 10, but it happens pretty slowly. So the bigger t is, the faster the graph will approach its capacity. Now, if you zoom way in, you can see it has a starting amount here. So this would be it starts at 0.159 and then grows up to 10. So what I want to do is a few problems with the logistic growth. So let's see, birds in controlled habitat have a population given by this equation, where t is the number of years after the bird habitat was started. So this is like a bird sanctuary for some endangered bird or something. So the people who built it originally put in some birds, and then the birds are gonna multiply and stuff. So how many birds were put in initially? Well, to find that, you just have to do f of 0, because this is at t equals 0. This is one we could do pretty easily. Just 500 over 1 plus 83.3 e to the negative 0.162 times 0. Well, e to the 0 is just 1. So this is 500 over 84.3. And when I put that in my calculator, 500 over 84.3, I get 5.93, which I'm going to say that is 6 birds. All right. What's the upper limit of the number of birds in the habitat? That part's easy. It's just 500. So that's the capacity on top. And this last one, how long will it take for the habitat to grow to 80% of its capacity? Well, let's see, 80% of its capacity, that's 0.8 times the capacity of 500, which is 400. So what we're doing here is we're going to put 400 in for the population equals 500 over 1 plus 83.3 e to the minus 0.162 t. You got to solve this for t. It looks like it's a bit of trouble, but it's not going to be that bad. All we need to do is, well, the first thing I'm going to do is divide both sides by 500. So let's see, over here, you can cancel this and get 4/5 equals 1 over 1 plus 83.3 e to that. Okay, now let's take the reciprocal of both sides. I mean, you could cross multiply. You could cross multiply. I guess we could have cross multiplied on the first step, but I'm going to take the reciprocal of both sides and get 5 over 4 equals 1 plus 83.3 e to the minus 0.162 t. Now I'll subtract this 1 from both sides. Negative 1 plus 5/4 is 1/4. Then I'll divide both sides by 83.3. So this side over here is, let's see, 83.3 times 4 is 333.2. So let's see, this side is 1 over 333.2 equals e to the minus 0.162 t. Then I'll natural log both sides. Or I guess to be proper, I should say take the natural log of both sides. And now I'll divide both sides of this by the negative 0.162 t. Or not t, just divide by negative 0.162. And stick this in the calculator. Let's see, ln of 1 over 333.2, close parentheses, divided by negative 0.162, gives me 35.85. years. So it'll take 35.8 years for this to grow to 400 birds in the population. All right. That's it for this section.